and welcome to the Fire in the Landscape Forum. My name is Tanya Ha. I'm a sustainability researcher and an environmental journalist, and I'm delighted to be your host for this forum. The Fire in the Landscape Forum is part of a suite of online forums that are being held as part of the Bushfire CRC Research to Drive Change project. Now, for a brief overview of today's forum, the focus is on the impacts of bushfires on ecosystems, namely water flows and quality, carbon pools and combustion products. We'll soon start with an introductory video, followed by 3 research presentations and some discussion with a lead end user. Along the way, there'll be online polls and opportunities for questions and discussion. Now, some of you are new to this online platform, so I'll introduce you to the environment that you find yourself in. It's fairly self-explanatory. The centre panel that you see there is where we'll present the slides and the videos. The right-hand column that you see on your screen is where you'll see the presenters via webcam. But importantly, I'd like to direct your attention to the bottom left-hand corner of the screen, where we have a dialogue box. You'll see it there with a talking balloon in its top left-hand corner. And this is the place that you can type your comments and questions as we move through today's proceedings. Note that our voices are coming through phone lines, but the vision is coming via the internet. Now, we do this for optimal clarity, but without taking too much bandwidth. But it does mean that there can be a little bit of a time delay between what you see and what you hear. We apologise for that, but we think it's the best that we can do with the available technology at the moment. Now, if anyone is experiencing technical difficulties, you can contact the hotline on 1800 733 416 and tech support will assist you. Now, that number again is 1800 733 416. One other minor note is we have found that the Bushfire CRC website has been offline a bit today. We're working to get that back online as soon as possible. Finally, the forum will be recorded and it will be available from the website at a later date. So if you do have colleagues that you think would benefit from the research that you hear today, do let them know. And incidentally, our last Research to Drive Change forum, which was on the community understanding of fire risks from living in urban-rural interfaces, that is now available online. Now, thank you to the people who have sent through some questions already. They'll be addressed during today's proceedings. And we'd also like to welcome several international visitors that we have joining us online today. I believe we have participants that are viewing from Brazil and Italy. So welcome, and we'll try not to sound too Australian with our accents. Now, it gives me great pleasure to let you know who you'll be hearing from today. We're going to have presentations from Dr. Taryn Turnbull from the University of Sydney, Dr. Peter Nyman from the University of Melbourne, Dr. Chris Weston from the University of Melbourne, who'll be joined for questions and answers by his colleague, Dr. Luba Volkova. And finally, we'll hear from a lead end user, Dr. Adam Leavesley from ACT Parks and Conservation Service. But to kick things off, we're going to start with an online poll. How much do you think you understand about the impact of fire on water and carbon? Do you feel you know nothing, a little, a fair bit, or a lot? Click on the poll and let us know what you think your knowledge level is at right now. And we'll give it a few more seconds. And we'll leave it there. So it's good to see that you feel that you know a little. No one said nothing, which is always good to have a basic understanding. And we hope that by the end of today's proceedings, you'll have a more solid understanding of not just the research, but what you might go to for more information at a later date. Now, before we start off hearing the presentations, we're going to have a short video that's been produced by the Bushfire CRC. This will introduce you to today's subject matter and the people we'll be hearing from later.
Fire management is not a physical problem in terms of the risk is actually to people and to society and assets. Yes, it's got physical elements in terms of fire behaviour and fuel and buildings, but in reality to solve any problems or to reduce risk, it's actually where social science and the physical and natural sciences intersect.
We're in a rapidly developing field of examining, in the aftermath of major disasters, the environmental factors that contributed to destruction. It's often assumed that things like people's aesthetic preferences, their attitudes to the value of bushland as habitat and ecological values, etc., are somehow fundamentally at odds and lead them to exist in a high-risk state. You know, that those values that underpin amenity are somehow preventing people from taking action. In fact, what we found was that people prefer bushland around their property in a condition which is relatively low fuel, which is quite open, and which actually corresponds or translates into also preferred states for recreation and aesthetics. So fundamentally, there's not evidence of a really strong conflict between the state of fuel, which is what we call typically fuel hazard, which is a key element of the risk, and their preferred condition of the vegetation in terms of their amenity.
It should actually give us better, more tailored outcomes if we can work either with supporting community values or directly with the community in trying to design bushfire management measures that are both more acceptable to the community and also protect the values that they actually value, rather than what we think they value. So it should give us better outcomes in the longer run, even though it may be more complicated getting there.
Basically all the houses are gone. It's just terrible. And then the 2 primary schools have gone in town. As I said, the restaurant, the hardware store, 2 restaurants. And yeah.
One of the things that we do, especially because we live in largely urban environments, is we reinforce that divide between nature and culture, and we think about controlling or commanding nature to give us some way of inhabiting the spaces that are important to us. Because our interest in this research group is in landscape, we were interested in thinking about how that social and ecological world came together for people, because it seems like in the government end, they're aware that there's this social aspect to living in the landscape. That's the conundrum, but the mitigation that they enact is usually all around managing the ecology, or managing the nature part of it. And we wanted to bring that nature, color, and culture bit together, and thought about how to develop a method that actually physically did that during the interview process. So what we got them to describe is what they did in a week in that landscape. So, where do you go? How do you do it? Why do you do it? Where do you go for a walk? What do you do? How do you look after those cows? What did you do? How do the kids go to school? And then introduce the element of risk into that. So, how does this work when there's a fire? What do you think about this in relation to fire? So in that way, they established how they live in the landscape first, and they vocalized it, which is something people don't do all the time. Once they have their regional map on the thing, they're talking about it as a landscape, that they understand that they're not living in isolation. And that's something really interesting, because most messages are just targeted at the householder.
Fire suppression is possibly close to its limits. We don't have a lot more resource to throw at it. Technology will make improvements, but some of those landscapes, there will be fires in the future. We can't stop them. As we engage with the community on different issues, here's some tools that will help facilitate better conversations, and largely that's what's happening, is we need to have stronger conversations with the community to find the win-wins.
And thank you to the Bushfire CRC for that video. It can be viewed online either at the Bushfire CRC website when it's back online, or also via YouTube in that link that I just went through. And for anyone who did have trouble hearing that video, then I'll give you a quick overview of what it covered. It looked at a discussion of how prescribed burning and wild bushfire affect water quality and quantity, and in the case of carbon, how burning affects plant growth and carbon and smoke products in the atmosphere. Importantly, some of the researchers also considered different forest types, mountain ash, for example, compared with mixed species forests. Again, that video can be viewed online if you had any trouble viewing it. It now gives me my great pleasure to introduce the next speaker, or the first presenter, which is Dr. Taryn Turnbull from the University of Sydney. Taryn's going to be talking about fires and the hydrology of southeastern Australian mixed species forests. And again, for the audience, we encourage you to send through your comments and questions via that dialogue box that we have at the bottom left-hand side of the screen. Take it away, Taryn.
Excellent. Thank you, Tanya. So, I've immediately gone too far. In Australia, anywhere between 50 to 90% of water to fall on a catchment will be transpired back to the atmosphere by eucalypts. Our catchments are vegetated with two main forest types. We've got ash forests and mixed species forests. The hydrology of the ash type forests is much better known. For example, we didn't know much about the patterns in tree water use after fire in resprouting mixed species forests, or the biology of the canopy in that forest type as it regenerated after a fire. For this project, we had four aims. We were going to determine the patterns of water use in mixed species forests as they regrow after fire, characterise the canopy biology during that period of regeneration, test existing models for predicting tree water use in this forest type, and develop a simplified model that would enable agencies to estimate tree water use. As catchment yield is strongly dependent on the capacity for trees to use water, catchment yield is vulnerable to any event that modifies the structure or the biological processes in a canopy, such as fire. Catchment yields are rapidly decreased after fire in ash-type forests, so within the first 7 years after a fire, catchment yields are 50% below what they would have been before, and these reduced yields persist for decades. The mechanism in that forest type is well understood. Ash-type forests they regenerate prolifically after a fire from seed, and the seedling-dense regrowth has a much greater proportion of sapwood, and that's the tissue that conducts water, than its mature counterpart. Additionally, leaves on young eucalypts are also different to those on mature eucalypts. They have this leaf form called juvenile, and their juvenile leaves are predisposed to greater rates of water loss. But mixed species forests regenerate differently than ash-type forests after a fire. They can also regenerate by seed, but they also regenerate quite often by release of epicormic buds that are located along the entire length of the tree bole. The impact of that life history strategy, that is regenerating by epicormic sprouting, on catchment yields was undocumented before our project. So our research uses a variety of approaches to investigate the key components of canopy biology, and that's the primary driver of tree water use, which we call transpiration. So for the first 3 years after the 2009 Black Saturday fires, we conducted month-long campaigns in April, so that was April of 2010, 2011, 2012 as well, in a burnt area in northeast Victoria near Beechworth. For the two most prevalent eucalypts in that forest type, we quantified canopy leaf area and patterns of leaf distribution, leaf gas exchange within the canopy, and that was gas exchange of water and carbon, and also structural constraints to leaf water loss. And even though I'm terrified of heights, we still managed to do a decent job. So leaves resprouting on epicormic branches are initially of the same juvenile form as those that we talked about from regenerating ash-type seedlings, but leaves on epicormic branches revert to adult form much more quickly than those in seedlings. So you can see this transition in between 2010 and 2011 on our data set. That's the two clumpings of groupings on the inset graph there. All 5 anatomical features we measured on leaves as they resprouted from fire were consistent in showing this trend. So they differed structurally and they also differed physiologically. The leaves produced 1 year after fire were energetically less self-sufficient, so they had a reduced capacity to photosynthesize, but they also had a greater rate of carbon lost by the process of respiration. We used isotope analyses coupled with these measurements to investigate whether leaves on resprouting epicormic branches differed in their capacity to lose water as the canopy reinstated. And you can see by the graph that delta 13C, and that's the graph on the right-hand side, was unchanged for that period, 3 years after the fire. So what we can say from that is that the relationship between photosynthesis and the capacity for a leaf to lose water was constant. So we can assume that the leaves that sprouted immediately after the fire actually had a reduced capacity for water loss because they had a reduced capacity for photosynthesis. The second part of our project, was to compare those findings to what we see in a mature, unburnt mixed species forest. So to answer this question, we set up a second experiment to quantify tree water use in mixed species forests that were also burnt during the Black Saturday fires, and we compared those burnt forests against their adjacent mature forest that was unburnt. So as briefly discussed before, tree water use depends on the prevalence of sapwood, and you can see that as the red part of those bands around the trees on the left-hand side of the slide there. The speed of sap flow, which we measure using a sap flow probe, which is in the top right-hand corner. The leafiness of a forest, and you can see an unburnt mixed species forest on the right panel down the bottom, and a burnt mixed species forest in the middle panel. And the evaporative demand of the atmosphere, and we measure that using the micrometeorological station that was also shown there. So we quantified sap flow between 2011 and 2012, July to July for both years. Evaporative demand, which is the main control of tree water use, was greater in the unburnt mature forest, and soils were wetter in the burnt regrowth forest. But overall, rates of tree water use were very similar in the burnt regrowth forest to the unburnt mature forest. This clear difference in tree water use between resprouting mixed species forests and ash-type seedlings results from 3 factors we found. There was little increase in sapwood area in species that belong in regenerating mixed species forests, so they only had a 20% increase in sapwood area compared to a 70% increase which happens in ash-type eucalypts. There was a decrease in leaf area after fire in mixed species forests, whereas it normally increases in ash-type forests where it's regenerating by seedlings. And we also documented a slower sap flow in regenerating mixed species forests, whereas it's unaffected by fire in ash-type forests. So the next thing we had to do was to model our findings. First, we tested a well-known model, SPA, which is a process-based model that simulates processes between soils, plants and atmosphere, including evapotranspiration, soil energy fluxes and growth primary production. The scale of parameterization of that model is at the leaf level, whereas it predicts tree water use at the canopy level. So its main benefit is that it allows for scaling up processes. We found it was able to predict transpiration in these mixed species forests, but it was still limited use for agencies that manage forests for catchment yield. It requires 20 separate inputs to parameterize it, and a lot of them are quite labour intensive. It would be a very expensive exercise to parameterize forest water use using that particular model. So we set about making our own. We developed a model of tree water use that was based on the influence of light and evaporative demand, which are 2 environmental variables easily obtained by the public, on stomatal conductance. The model we made accounted for 89% of the variation in tree water use, and it just requires a brief period of training, which can be no more than 1 month of installation with sap flow sensors for a particular forest type. We've already instrumented it in 4 main forest types within the catchment, so we're pretty confident that it's robust for these ones. The main research outcomes we had was that fire is likely to affect water cycles very differently in mixed species forests than it is to ash-type forests. The initial flush of juvenile foliage that happens after fire in resprouting eucalypts didn't heavily transpire, and the subsequent increases in capacity for a leaf to use more water was countered by a reduction in total leaf area. So for a few years after Crown removing fires, water use by resprouting mixed species eucalypt forests was little different to the nearby mature mixed species forests. But because we found that the leaves that were produced during the first year after fire had a greater respiration rate and a reduced photosynthetic rate, we say that successful regeneration may depend on the health of the forest before the fire. So this project was a collaborative one. It was between Mark Adams, Tom Buckley, Ali Barlow, Mana Garuna, myself, and we received expert technical assistance from Michael Kemp throughout the whole time. Thank you. Back to you, Tanya. Sorry.
Thank you, Taryn.
You're welcome.
Look, the thing that strikes me as really important about this research is that perhaps before it was done, people tended to take a one-size-fits-all with their understanding of forests and ecosystems and their effect on water flows. Can you tell us a little bit about the importance of considering the type of ecosystem and making sure we have information in Australia and internationally that is locally relevant?
Thanks, Tanya. So the main thing is these two forest types are equally proportionate in our catchments, especially in the ones around Melbourne. There's 50% of the catchment is made up of the ash type, 50% is made up of the mixed species forest type. So if you just assumed that the mixed species forests responded to fire in the same way as the alpine ash or the mountain ash forests, then your calculations of yield could be greatly out. That's the main thing. It's just a tool for land managers.
And I guess too, if these are catchments that flow into Melbourne's water supplies, then you want those estimates to be correct in planning, don't you?
Absolutely. Yeah.
Well, we'll leave it there and introduce our next speaker. Thank you, Taryn.
Thanks, Tanya.
The next presenter we're going to hear from is Dr. Petter Nyman from the University of Melbourne. Petter is going to present on quantifying the risk to water quality. And again, we encourage the audience to send through their questions through that bottom left dialogue box. Take it away, Petter.
Thank you, Tanya. So my work here is on quantifying risk to water quality as a result of post-fire erosion. The work is a collaborative effort between myself, Gary Sheridan, Renee Vanderstant, Phil Knoxville, Chris Sherwin, and Patrick Lane, and they've all contributed to that. In this part of the world over the last decade or so. Both the Sydney and the Canberra water supply catchments have been burnt as part of these fires with large impact on water quality. In particularly, the catchments near Canberra were affected quite strongly by the wildfire in 2003 with large increases in turbidity and constituents such as iron and manganese. Ultimately, these impacts resulted in disruption to the water supply and investment in a new treatment plant at the cost of about $40 million. This graph here that I'm showing in the slide is taken from a study by White et al. In the Journal of Water Resources Research, and it shows the turbidity in the coastal catchments in a 30-year period between 1975 and 2005, and you can see the big spikes in turbidity following the fire in 2003. It's about a increase by a factor of 3 or 4 in turbidity, and I think the manganese and iron increased by a factor of 30. Another example of the impact of fire on water quality can be seen in this data from Lake Maggie in Victoria from a wildfire in 2007. So this data actually contains the impact of 2 fires. So the data spans back to 1990 and through to 2010, and the headwaters of the Lake Maggie were burnt in 1998, just a small part, 17%, and then again in 2007. And the black dot there is the nitrogen, and the clear dots is the total phosphorus content in the water entering Lake Maggie. And you can see there in the data that's shown that the area burned is really important. So in the 1998 wildfire, there's only or hardly an impact at all. But then in 2007, both nitrogen and phosphorus increased to well above the guidelines for water quality in fresh water set by Australia and New Zealand standards. So post-fire erosion response can be very complex to predict because you have variable fire severities, different intrinsic catchment properties, and randomness in the type of rainfall events that you see after a burn. So we need models to try and untangle the effects of all these different variables on risk. And models have applications in different to different land management questions. So we can, for instance, produce a metric with baseline risk, so the frequency and magnitude of impact. We can also provide a basis for developing risk maps, so using maps to show the relative risk in different parts of the landscape. And also more sophisticated models can be used to identify the effects of different management interventions. So for instance, if you're wanting to mitigate the impact of a burn on a hill by putting out hay bales, you might be able to use models to see what the effect of those measures might be. And different management questions require different types of models. So, and temporal scale is really critical to understanding how models address different land management questions. In this little figure here, you have 3 different temporal scales. One is within an event. The other temporal scale is during a recovery from a burn, so a 5-year time frame, and the other scale is a 100-year time frame. So each of these time frames have different types of parameters that determine what type of erosion, what type of risk you need to predict. So within an event, you're interested in the actual rainfall event and the type and the intensity of that storm in relation to the burn impact. Whereas within a recovery period, within a single burn, you're interested in the rate of recovery of a catchment in relation to the number and severity of storms during that period. So your risk picture becomes more complex. And then over sort of 100-year time scale, then both your fire regime and your rainfall regime are variable, and you need to incorporate more information on the frequency and severity of fires, as well as the frequency and severity of storms in the landscape in order to determine the risk of water contamination. So in our research, we set out to explore or develop models for incorporating these fire and rainfall regime parameters into measures of risk, and then follow up with more experimental work to look at how fire severity and aridity act as landscape filters in determining how the interaction between fire and rainfall regimes translates to erosion. So this first research outcome is related to the model development. So this is just a quick summary of the type of model that we developed to predict the effects of fire and rainfall regime on water quality risk. So the blue discs in this figure represents rainstorms, and the red disc represents fire events. And the discs have an area, so an X, Y direction, and they also have a duration. So for storms, the area is about 10 kilometers squared, and they last for about 30 minutes. For the fire events, they have variable areas, and they last for about 2 years. So we're not interested in the duration of the fire itself, but the duration of the fire impact. And using information on the area and the duration of burns and storms, we can say something about the expected annual area of intersection. This annual area of intersection is directly proportional to the frequency with which a landscape is primed for a particular erosion response. So these parameters we can obtain from the Bureau of Meteorology for the rainstorms, and then for the size and duration of, or size and frequency of fires, we can work with fire history data to obtain those parameters. And as a case study, we've used this model to look at the frequency of debris flows in Victorian and catchment, and in catchment in Canberra, near Canberra. And we know that the rainfall thresholds for these large debris flow events, which Terry Sheridan pointed out as being a really important process in the video you saw before, the rainfall threshold for these events is about 35 millimeters per hour. And modeling these rainfall events together with the frequency and size of fires, we can say something about how often we're likely to see these large events occur over long time scales in the landscape. So for current fire regime, I'm trying to find the pointer here. Here we go. So you see these green lines here are for current fire regime. You can see that for storm event rates representative of Kilmore, north of Melbourne, you're likely to see an event frequency of about 250 to 400 years. And for a more intense fire regime or storm regime in northeast of Victoria near Bright, the more frequent storms means they also have more frequent erosion events. And then we can play around with climate change, for instance, and say, if we change the size of fires, how is that going to influence the rate at which these events occur in the landscape? So by adjusting the fire frequency for a high climate change scenario, we can see here that your frequency ends up being much higher as a result of more frequent fires. So it reduces by about a half. You get twice as more frequent storms with climate change impact on fire regimes. Now, for understanding how these fire and storms actually translate to our response in the landscape, we need to know how fire severity affects response. To do this, we instrumented some headwater catchments with these tipping buckets and measured surface runoff for wildfire, for prescribed fire catchments, and for unburned catchments to see how the peak discharge is dependent on fire severity. And these are the results. So they're quite clear patterns in terms of how fire severity affects peak discharge. On the y-axis here, you have peak discharge. On the x-axis, you have rain intensity. So as the rain intensity increases, your peak discharge increases. And for wildfire, this dependency is much stronger than it is for prescribed fire and unburned conditions. We use peak discharge as a measure of response because this is directly proportional to the amount of sediment that you're likely to see coming out of these catchments. Next, we were interested in understanding how landscapes vary in terms of their sensitivity to fire. And we used aridity as a measure of sensitivity because aridity affects the soil. So for more drier environments, you like to see poorer soil formation, soil development, more rocky, more gravelly soils, and therefore more surface runoff after fire. In wetter environments, the soils are more productive and we tend to have much more infiltration, which reduces the potential for post-fire erosion. So we set up some plots in different levels of aridity to see how the runoff varies with aridity. We have a very clear trend here in how much runoff is produced for different aridities. So in an ash-type forest, you have runoff production of about 5%, whereas it's almost 30% for dry mixed species forests in the upper end of this aridity spectrum. So how is this useful for management? Well, we're providing information to inform strategic land management decisions by providing a model which will help land managers evaluate the changes in water quality as a result of landscape processes such as climate change, prescribed burning, and rainfall regimes. And our plot here of the average return interval of different of debris flows as a result of climate change is an example of that. For operational land management applications, we can provide information on the spatial aspects of risk. So where, for instance, is prescribed burning likely to cause risk to water quality? And during a wildfire, where should we focus firefighting efforts to reduce the risk of higher value assets and where the risks are higher? So this is an example of these type of risk maps that we produce for the Melbourne water catchment. This is the Upper Yarra, and these red areas are areas that are high risk in terms of their propensity for producing debris flows. So in summary, we've developed a model for evaluating the effects of fire and rainfall regimes and erosion frequency. We developed quantitative relations between fire severity, rainfall, and runoff response. And then we have developed a basis for using aridity as a metric of landscape response to fire. And all this information can be used to produce models to inform both operational and strategic aspects of land and fire management. Thank you.
Thank you, Peter. Now, just while my camera comes back on in a moment, I've gathered you can hear my voice, so here I am. We've got a question that's been sent in from Kathy earlier, and a reminder to the audience, if you do have some questions for Peter, you can type them in the dialog box at the bottom left of the screen. Kathy has asked, with the uptake of plant growth after a fire, does the water quality improve compared to before the fire within, say, a 2-year cycle?
So the main effect of plant growth after fire is, one, it stores water, so you have less water actually hitting the surface. It protects the surface from the impact of raindrops. And also it creates more roughness. So once you produce overland flow, the plants actually reduce the amount or the velocity of the flow across the hill slope. So we haven't actually measured the effect of post-fire vegetation on erosion relative to pre-fire erosion. But if the vegetation cover on the ground is very dense compared to what you would see in a pre-fire setting, then it's possible that it might reduce the erosion rate relative to background conditions.
Is that an area for future research, do you think?
Yeah, I think the main question that we should be addressing with future research is more around how long it takes for different systems to recover. So, you know, different levels of aridity mean different rates of recovery. So dry environments take long to produce that type of vegetation, which prevents erosion, whereas wetter environments recover more quick. So actually trying to understand how that recovery varies in the landscape is probably more of an urgent question in terms of research needs.
And I guess with projections for climate change, that's going to be an increasingly important and difficult thing to study as well.
That's right. That's right. So with climate change, you both have these changes in rainfall and fire regimes superimposed on changes in the actual landscape itself. So you have intrinsic catchment properties like soil, vegetation, and feedback with erosion that might change as a result of increased fire. So there's a lot of complexities there to untangle, and obtaining the data is very difficult because these processes operate over timescales which are hard to do with experiments over 1 or 2 years.
Yeah. Well, thank you, Peter. We'll leave it there. It's my great pleasure to now introduce our next speaker. We have Dr. Chris Weston from the University of Melbourne, and at the end of Chris's presentation he'll be joined by his research colleague Luba Volkova for the questions and answers session. Chris is going to be speaking on the topic of forest carbon balance and emissions management. Thank you, Chris.
No, thank you, Tanya, and good to be part of this online conference. So our task as part of this project was to put some numbers on the board for the impact of fire on forest carbon and the emission of some key greenhouse gases. And the background to the project really is that there wasn't very much known in terms of the impact of either planned burn, and indeed there's not much known about the impact of wildfire or unplanned burn on the carbon balance of forests in the short term or over the long term. So our aim was to measure the immediate impact of prescribed burning on carbon balance across a range of open forests in which we typically apply planned burning operations. And we attempted to cover a range of burn conditions. Our second aim was then to apply this knowledge to develop a better knowledge base to enable end user agencies to both model the immediate consequences of prescribed burning on carbon and greenhouse gases, but also to consider the development in a policy context of the importance of planned burning overall in minimising the impact of burning, unplanned burning in forest landscapes. So a little bit about the background to the study. We know that the weather is getting warmer, and we know that there are more extreme fire danger days predicted to come in the near future. Indeed, they've probably already arrived in the last decade or so. Across much of southeastern Australia, there have been 3 large megafires, or 3 megafires in the last 10 to 12 years. And just simple back-of-the-envelope calculations show us that emissions from these megafires in the southeast have contributed, or could possibly have contributed, to 10% of Australia's annual national emissions. So what this means is that a small change in the forest carbon stocks across Australia can lead to large impacts in terms of our annual emissions reporting. So to improve knowledge in this area, we set out to improve this database of all carbon pools that are potentially affected by fire. And our aim really was to follow along and do a similar type of job to that which has been done for the top end of Australia, where there's been a concerted effort to look at the impact of fire on forest emissions in the trees over grass systems in the north. Our approach was a relatively simple one. We aimed to do field-based measurements of forest carbon before and after fire, and to try to cover a wide range of forests across the southeast, from southern Queensland through to some fairly dry and low productivity forests in South Australia and also in coastal Tasmania, as well as some medium to reasonably high productivity forests in the wetter parts of the moist lowland forests of Victoria. Over the life of the project, quite a few plots were measured, and we interacted with a broad range of agencies, and along the way we managed to transfer the knowledge of measuring forest carbon to over 40 or so staff who were essential in completing the project. So we thank the staff from the many agencies that participated. We've tried to summarise the distribution of forest carbon in just one slide to convey to the audience that our knowledge of forest carbon up to this point has mostly been that which is in the stems of trees, which are of interest in the harvesting and merchantable timber operations in forests. This makes up most of forest carbon above ground. Between 60 to 80% of carbon in the forest is not accessible by fire and resides in the stems of trees that are resistant even to some of the more intense fires that are typical in wildfire situations. Our aim really was to put numbers on the amount of carbon that is contained in the ground flora, so the ground layer, the litter and the coarse woody debris of the forest floor, as well as the near ground fuels that comprise the ground cover and the understory. So you can see from this slide here that across the broad range of forests that we looked at, and we've summarised them here by states, that on average above ground forest carbon is around about 165 megagrams of carbon per hectare. Most of this, as you can see, resides in the overstory. And we've also accounted in this slide to carbon down to 30 centimetres depth. And largely it's the understory, the ground cover, the dead wood of snags and coarse woody debris, and the litter which is impacted by fire. Soil carbon is not impacted by planned fire to any great extent, and it's really only in wildfire situations that surface soil carbon becomes a concern in terms of losses. So we're now in a position where we can advise the agencies of the typical range of carbon losses that they can expect from planned burning operations in open forests. Here we see that the average loss of above ground carbon from planned fire is around about 7 megagrams of carbon per hectare, equivalent to somewhere around 3 to 5% of the total carbon in the forest. You can see the range there extended from 3 to 11 megagrams of carbon per hectare. We also, in an attempt to, or in our future plans to model carbon losses at a landscape scale, we were interested in relationships between forest productivity and carbon losses, and we now know that carbon losses decrease as a percent of above ground biomass as forest productivity increases. And we can use these relationships in the future. We know that carbon losses increase with fire intensity, which is a reasonable conclusion. However, we're able to put some numbers around the impact now of the difference between planned and wildfire on some of the key fuel losses. For example, litter, which is generally averages around about 67% loss in a planned fire, it increases to 90% loss in a wildfire. Coarse woody debris is activated in particular by wildfire conditions, and one of the key outcomes from this project was to put some numbers around the coarse woody debris losses from planned burning in the range of forests that we looked at. And dead standing trees also become far more a source of carbon loss as fire intensity increases from planned burn situations through to the typically very intense fire conditions of wildfires. We are able to advise the agencies of some fairly straightforward measures to reduce or minimise carbon losses and emissions from planned burning. These include protecting the significant amount of, potentially significant amount of carbon loss, potentially significant amount of carbon loss from coarse woody debris and standing dead trees can be minimised by raking around them prior to burning, planned burning operations, especially if the forest area contains large coarse woody debris pieces, then these can be targeted for mitigation actions. Other actions to decrease carbon emissions include burning when the litter layer of the forest is reasonably dry on top, perhaps around 10%, but more moist underneath, closer to the soil surface. And we also established that it's important to account for loss from all carbon pools and emissions estimates. Currently at a national level, or Australia's international reporting of fire emission losses from forests is based on an estimate of fine fuels only, but we now know that it's important to account for coarse fuels as well to provide a more complete picture of carbon losses and emissions. And in ongoing efforts to improve Australia's emissions estimates from burning in forests, we now know that it's important to stratify the emissions by fuel type. And we've got a strong basis now to separate forest fuels into fine and coarse components to do this and to ascribe emissions factors to each of those to more accurately reflect the true emissions resulting. And finally, perhaps in a more detailed area of the research that we looked at, we know that there is a significant amount of carbon redistributed in the forest during burning operations. And in terms of forest floor carbon, depending on the intensity of fire, long-lived carbon or char carbon or char production, char is either created or destroyed by fire, and as the fire becomes far more intense, then char production is decreased and you actually get a loss from the char carbon pool. So in this context, planned burning is a far more beneficial outcome in terms of carbon storage than the intense wildfires that can lead to loss of carbon from this pool. So I think I'll leave it there and open up for questions. Thank you.
Thank you, Chris. And we're now getting Chris to move over a little bit so that we can welcome Luba to join him for questions and answers. Hi there, Luba. Thanks for joining us. Peter Marie has sent through a question. How should fire intensity be reduced in prescribed burns to minimise carbon losses?
Okay, so if planned burning results in a mosaic of burnt and unburnt patches on the forest floor and throughout the forest area treated. So at least in the state of Victoria, the idea is to go for a fairly low intensity planned burn to burn off the more readily combusted fine fuels and a component of the ground cover and near surface understory. And losses can be minimised through this approach, or can be further minimised through this approach by, as mentioned during the discussion, by raking around especially some of the larger coarse woody debris or perhaps standing dead trees on the site treated.
I think it's more about fine fuel moisture if we talking strictly about fire intensity, because fire intensity influenced by fine fuel moisture. And I think all land managers actually can only burn under specific moisture conditions between 15 to 10%. So when we reach in 10 and lower fuel moisture, then fire intensity increases. Therefore, simple answer, fire intensity can be reduced in prescribed burning if you burn under optimal fuel moisture conditions.
And is that something that's difficult or easy to monitor, to check?
Well, that's what land managers do anyway, and I think Adam would be the best person to answer because he's a land manager who is doing this as everyday job. But yeah, they do it pretty accurately. Now they have little good machines they can carry in the bush and monitor when the fuel reaches some optimal moisture level to start their burn.
Well, we might revisit that with Adam when we hear from him shortly. Peter, all the way from Italy, has sent through a question earlier. What practical consequences does the investigation have for landscape management in general?
I think in a broad context, we know that we can apply planned fire and know the carbon and greenhouse gas emissions consequences of the fire that we apply. And that's very important when it comes to the application of fire in an environment where the climate is changing and where the risk of large and uncontrolled fires is increasing. So we've just outlined some of the practical measures which can be used to minimise carbon losses and emissions during planned burning. As this knowledge can be applied in a strategic and a management context over longer periods of time to justify planned burning rather than allow the forest to experience a higher risk of wildfire.
Do you have anything to add to that, Luba?
Well, I think the question was about what's the practicality of this research. And what we want to highlight is that now we can very accurately estimate impact of fire, wildfire and prescribed fire on carbon and emission only because we start accounting for char production and for different fuels. And we can see that it's actually affecting land managers negatively because wildfire, now the, how to say this?
We've provided the evidence for
mitigating potential of plant fire over wildfire because of accounting for charcoal and for accounting for contribution of coarser fuels into the fire, overall fire. I think that's one of the practical outcomes and most important from this research.
Well, thank you. We might leave the questions there. Now, we've now heard from all of our research presenters. Before we hear from our lead end user, we're just going to run a quick poll to gauge an understanding of how you, the audience, might use the research and information you've heard from today. So we're asking you to give us your general feedback rather than making formal commitments. Just let us know, and you can answer more than one choice in this poll. In which ways could you begin to use what you've heard today? 1, share and discuss this with colleagues and stakeholders. 2, use the findings to inform policy and practice in my organisation. 3, advocate for more resources such as funding for your organisation. And 4, learn more about how I can apply this work to my role. And we'll give it a few more seconds. And we'll leave that there. Thank you. And it's interesting to see the mix of the ways of using that information, both internally amongst an organisation and externally amongst stakeholders as well. It's always good to see how these things can be applied. Now it's my pleasure to introduce Dr. Adam Leavesley. He's our lead end user today. He's from ACT Parks and Conservation Service. And Adam's going to discuss in general terms his position and the perspective that he brings to today's research. And Adam, generally, what are your impressions of what you've heard about today and how they can be applied?
Thanks, Tanya. Representing the lead end users, we're extremely happy with the process that we went through in getting to this position and really happy with the outcomes of the research. I've been involved with the CRC from near to the outset as a student in the beginning. And one of the things that was evident in the beginning was there was quite a tension between the need for sort of novelty and innovation amongst the researchers and some of the industry expectations about what was what was possible. And I think through the time of the CRC, there's been an adjustment in the expectations of the end users and greater accommodation of the needs of industry amongst the researchers. So we get to the end of a project like this and we've got a range of outcomes that are extremely good, extremely useful, and will make a great deal of difference to the industry, especially in the southeast of Australia. The story in relation to mixed forests and the amount of water yield following fire is extremely important for us in the ACT and for other parts of Australia, because within the ACT, the ash-type forests are perhaps less than 10% of the land area. So if you were assuming, of the catchment, so if you're assuming that the water supply that was coming from them was the same as the mixed forest, you'd be making big mistakes. So although they hadn't been studied at all in the past, and we've got a much greater understanding over the southeast of how we expect water supply to change following fires over a much larger area. The study that Peter Nyman did looking at erosion following fires, that's really important for the industry. We've initiated a research utilisation project via AFAC, and we're trying to develop guidelines for managing fire and erosion that will be applicable right across all the agencies, all the AFAC agencies, that's Australia and New Zealand. The carbon research that Luba and Chris did, that's also extremely important. It's a key issue in Australia and all over the world. If we had have found that planned burning was having a really strong impact on the amount of carbon that was being released into the atmosphere, then that would have been something that we would have had to take into account of. But the results that they came up with suggest that the burning programs potentially can be used in a way that will be positive in relation to carbon. So that's a really important finding for us. In a nutshell, we understand a lot more now the consequences of putting planned fire into the landscape, and that's an excellent position to be in. What I'd also like to say is that my boss here at ACT Parks, Neil Cooper, and Dr. Tina Bell from Sydney University put a lot of work into administering this program, that dirty work no one wants to do, behind the desk, accounting for funding and all of that kind of thing, and they really should be given a big pat on the back and thank you for getting the project to where it got to today.
Credit where credit is due. Thanks, Adam. What changes do you think need to occur within the fire and emergency management sector to take up the findings into policy and practice?
That's a really interesting question. There's a really important improvement was the thing I spoke about first of all, that we've managed to bring the researchers in the industry a bit closer together at the outset of this project, so that the things that people have been studying in this case are high priority for the industry. We want to know about it, and we've still got to, well, the research utilisation projects, that's things that we're still learning about how we can best do that, how we can put it in, bring it into the manuals, bring it into policy, bring it into changing the most appropriate ways that we can do that. But it's part of the learnings. Not only do we need new knowledge, but we need new research, but we need also to develop new systems within the industry to best use it. But I think a key change that we've seen through the period of CRC, we love our jobs. We do stuff that people pay to do on a day-to-day basis. I have no trouble getting a car. The cars are all parked out here, and I can go driving in the bush behind the locked gates. We get helicopters and we have a great time. But the point is that's not necessarily going to be the thing which leads to improvements in bushfire management. And I think over the period of the CRC, people have come to learn that we need to look at new ways, this new information and new ways of confronting the issue, sometimes not as fun on a day-to-day basis, but that a lot of the outcomes are going to relate to that sort of planning and understanding the landscape and spatial analysis and all those sort of things which allow us to do a better job So I think that's the key. It's happening, and we're going to only see better outcomes as time goes by.
That's an important point to make. Thank you for that, Adam. We did have a question sent in from Alan. He's asked, why would there be a difference between planned and unplanned fires in water quality and quantity in catchment forests?
Well, that's a good question. There's two, essentially there's two reasons. But first of all, well, I should say that what burns in a fire is material that was alive or used to be alive. And when you get a really hot fire, it's actually shocking to see trees that have survived the fire growing out of gravel. All the soil has disappeared, all the grass and the things you thought would have burnt have all disappeared. There's no leaves on the trees, but there can be no soil as well. And you can get a massive change. You get changes in the vegetation removed and the soil chemistry. And so, so there's no comparison between the fire severity in some of those really hot fires and what we can achieve during a planned burn. And then there's another aspect of that as well. When we're planning a fire, we don't burn it as intensely. We can also light it in places that prevent areas that might be prone to erosion from being impacted. And we can light it at times during a season, seeing the fuel moisture gradient across the landscape to try to make sure that we're only impacting areas where the effects on water quality and erosion will be minimised.
Which brings in the research that Chris and Luba were talking about as well. Look, that's all we've got time for. Thank you for that, Adam. Before we finish off today's proceedings, we're going to revisit our earlier poll just to see how our knowledge and our understanding of these issues has changed. So tell us, how much do you think you understand now about the impact of fire on water and carbon? Oh, it's concerning that someone said nothing, given that no one said nothing earlier when we revisited it. We'll leave it there. We are delighted to see the bulk of the bell curve move towards the bottom, which hopefully means that we've all learnt a little bit of something today. I'll now invite all of today's presenters back to the screen so that we can hear from them before we finish off. And just hearing from the presenters in order that they presented today, just give us your final concluding remarks, a thought for us to take home today from the proceedings. Sharon, we'll start with you.
Thanks, Tanya. So I think from our work, we need to understand how water is used by vegetation in forested catchments and how this is influenced by events such as fire. So our research adds to the knowledge base of just how different forest types use water, and it shows that mixed species forests use water in a completely different pattern to ash type forests, and that was something that was unknown before we started this project.
Thank you. And Peter?
Well, I guess one of the outcomes is, unfortunately, that we've seen how complex these processes are, and that the transient nature of fire effects and the randomness in rainfall and variability in intrinsic catchment properties means that data alone will sort of never be able to capture the full spectrum of risk that we'll see in the landscape. So the challenge, I guess, is therefore to develop models that are based on general concepts and having a model framework that align with some of the key questions that are being asked by the land managers. And also having models that are built around general sort of principles and laws which are transferable from one location to another, and that way maximizing the applicability and usefulness of type-specific research and to improve the way in which we manage risk and prioritize research across the landscape.
Thank you, Peter. Who would like to go first, Chris or Luba?
Always a difficult one. We think our research points to the need for an improved knowledge of fuels and of the types of fuels in forests, and the need for land managers to have a good monitoring database that is maintained through time and updates fuel loads as climates change and as burns occur, so that when fires do occur, we're in a good position to know how to deal with them in a behavioural sense, but also some of the emissions consequences of burning.
Mm. And Luba?
Yeah, I agree. Yeah, and another point which Chris was making is about importance of accounting for char production, because it's a long-term carbon storage, and once it's not accounted for, we assume that all that carbon is gone to the atmosphere while it stays in the ground. So it's a 30 to 40% overestimation of emissions rather than what happens in reality.
So more robust carbon accounting that accounts for the char as well. It is important.
For all fuels, yes. So not just stick to one fine fuel, but yeah, robust accounting for carbon.
And of course, Adam, the lead end user, gets the last say.
We think that one of the key learnings from the point of view of trying to get research that you can use in this sort of partnership is that you work as hard as possible to get to know the researchers, to help them to understand your business, and to bring everybody together, because that has led to the sort of results that we've got out of this project, and we've been very happy with. Going forward in the future, I think we've still got more that we can do in terms of research utilisation, and that's the sort of window, that's the space where this kind of project can be further improved again.
Thank you, Adam. Well, that brings today's forum to a close. I'd like to finish by thanking today's presenters, Taryn, Petter, Chris, Luba and Adam, and also to you, the audience, for your participation and your questions. We encourage you to visit the Bushfire CRC website at www.bushfirecrc.com. We do hope it will be online very soon. In the coming days, we'll make today's presentations and video available, and there'll also be fire notes on the website that relate to today's research that we've discussed. We do encourage you to invite your colleagues to watch and see this information at a later date if you feel that they would have benefited from seeing today's proceedings. We know we've gone a little bit over time, but if you do have a couple of spare minutes, we would really appreciate you staying online for a brief exit survey. If you could tell us a little bit of feedback, then we can use that to improve future research forums. Our next webinar forum will be Awake, Smoky and Hot, and that is going to take place on Monday, September the 22nd. Keep an eye on the Bushfire CRC website for details, or leave a comment in the exit survey if you'd like to be included in the mailing list for future events. On behalf of the Bushfire CRC Research to Drive Change project and its partners, thanks for joining us today, and we look forward to seeing you next time.